what we're going to do here, what have you guys been talking about? You guys been talking about
We're making liquid nitrogen
so
ice
you guys been talking about like phase changes and
Yeah.
states of matter? Okay. So we're going to talk about what's a few different things before we get into ice cream. Okay, so one of those is what's in the atmosphere. Oxygen's in the atmosphere, anything else in the atmosphere? Carbon dioxide and nitrogen. Is there water in the atmosphere too? Water in the atmosphere. Okay, so we call things, when they're water vapor, okay, is there a difference between vapor and liquid? So I got liquid right here, right? But there's water vapor in the air as well. We got water liquid, but then we have nitrogen. Is it a gas or a liquid? Gas. So why do we call it? So we know it can be a liquid. I can see right here that I have liquid nitrogen. So what makes that different than nitrogen? Gas. Why don't we call nitrogen liquid nitrogen? Like where water is water liquid.
Liquid nitrogen is in its liquid form, while regular nitrogen is in its gas form.
Okay. So let's say that everything like at room temperature is whatever it is. So is nitrogen room temperature? A liquid at room temperature? No, it's a gas at room temperature. So if we say, hey, I've got some nitrogen, and I don't specify liquid, it's at above a certain temperature. So nitrogen boils, water freezes, okay, at what level?
32 degrees.
32 degrees Fahrenheit or 0 degrees Celsius. But nitrogen boils, doesn't turn to a solid, doesn't freeze, but boils at 321 degrees below zero. So if I say liquid nitrogen, so if I specify liquid nitrogen, okay, it has to be what condition? It has to be below 321 degrees below Fahrenheit. Okay, so the stuff we get out of here is liquid nitrogen, so we're specifying how cold is it?
Very cold.
321 degrees below zero. So the cloud that we see, is not nitrogen. Nitrogen, when it turns to a vapor, it doesn't have a form like this. So this right here is water vapor. So we breathe out carbon dioxide, and we breathe out water vapor. Okay? So when I cool down my breath with the nitrogen, I get some water vapor. Right? So now, if I pour this out, it's going to hit the table and it's going to evaporate really, really fast. See, it's all gone. So if I poured in this water, where you can see it a little bit better in that container, we see that we got a lot of water vapor because it's water.
Guys, can you
Right.
stop?
So we got that water vapor. But you see how it floats? So what do we know if it floats? What do we know about it? Is it less dense? Less dense, so it floats. Things are less dense, they float. Right? So we know the nitrogen is less dense, so it doesn't sink. So carbon dioxide, dry ice, does it sink? It does initially, and then when it gives off its gas, it starts to float because it's less dense. So carbon dioxide is dry ice. Now dry ice is not that cold. I mean it's cold. Okay, but it's not nearly as cold as liquid nitrogen. Right? So what's the next coldest thing on that? Oxygen. So do you think if there's oxygen in the air and we get the oxygen cold enough, can we get it to condense into a liquid? Yeah, we can. So we're going to do that. So we're going to take some liquid nitrogen, put it in the bowl. Now it's colder than the oxygen. So if it gets the oxygen cold, okay, then it'll condense. Now when things condense, let's say that when gases turn into a liquid, that's condensation. Okay? So when they condense, they take up 600 times less space. Okay, so if we're able to get the oxygen cold, then it'll turn into a liquid and it takes up 600 times less space. Now it's really, really cold. How cold is the oxygen? This drip in my hand? Right, exactly. So it's really, really cold. Now, if I put this on my head, it's not going to make my head wet. Now, why is it not making my head wet?
Because it's a gas.
Because it turns to a gas, and it's not water. So that's one of the ways that we test. So let's do a test with a teacher. So does that sting? Yeah, it stings. So now, would water sting? No, it wouldn't sting. Does it make your head wet? Feel your head. Is your head wet? No, it's not wet. It's just cold. Okay? So it makes your head wet, or not wet, and it just makes your head cold. But it stings, which water wouldn't sting. Okay? So it does make your hair fall out. Sorry. Okay, after about 30 years, just kidding. It's not, I don't think this had anything to do with nitrogen. So, you had a question?
Can oxygen get cold enough to the ice?
It can, but it has to be in a vacuum. So there's an equation that we're going to talk about right now. If I can find it. So I get it back up here. So if we have this equation, okay? P equals T, pressure times volume equals temperature. Okay, so I'm going to take a balloon, and I'm going to put some molecules in that balloon. Now, if I drop the temperature, what's going to happen to pressure and volume?
It's gonna
Go down or up? Down. Okay, because there's an equal sign. An equal sign says whatever happens on this side happens on that side, right? So if temperature goes down, pressure and volume goes down. So now remember, when gases turn into a liquid, they condense by 600 times. And when they expand by 600 times. Now, this is a very, very big thermos, and so it's not cold on the outside, it's just cold on the inside. Okay, we got that. Now, what did I breathe into it? Carbon dioxide and, yeah, there's probably some oxygen in there, but water. Remember I breathed out water vapor? Right? I'm going to take this. I'll use this like that. Okay, so now I'm going to get this cold. So I'm going to drop the temperature. So it's condensing. It's condensing by how much? 600 times, right? Okay, now, remember to bring up. Okay, now if you look on the inside, you see that it just kind of drips off. But can you see, I don't have a flashlight, but if you can see that there's some liquid on the inside. And you see it rolling around there? But as you heat back up, it turns back into a gas. That's just the frost. Okay? So, I don't remember bringing a flashlight. Sorry. Yeah, if you want, if you don't mind. Well, I'm not sticking my hand in the nitrogen. I'm just pressing on the balloon to get it down in the nitrogen. Okay, so on the bottom, I want to light up the back of it so you can see the liquid that's in the bottom. Okay, so right down in here. So right there. Can you see the shadow? See that liquid? That's a liquid. And as it starts heating up, from the air, from my breath, it expands and then turns back into a gas. So the molecules didn't leave the balloon. A lot of people think where's the molecules go? They didn't go anywhere. They're still there. They just took up less space. So they become, yeah, they took up less space. So think about this. Molecules are kind of like keep falling away. So there's different personalities, but they react differently. You know, chemistry they have different reactions, like sodium reacts with a lot of things, but nitrogen doesn't. Okay, so there's different personalities. I like to think of like molecules. Anyway, but the point of the matter is, when molecules are cold, they kind of like to huddle up, and they take up less space. So when you guys huddle up, like you take up less space. Now stand up. Okay? Now try and get as close as you can get. Without falling. All right, now slowly. Now slowly. All right, wait. Slowly push your arms out. Not fast. You can move apart. Take up normal space. Arm down. Okay. And then move around so you can spin like this. Right? Now you see how much more space you guys take? Okay. So that's condensation and evaporation. Okay. So when the molecules condense, they take up less space. And when they evaporate and they heat up, then they start bumping into each other and start taking up more space. Okay? And we're good on time. So it's just a balloon. Just a regular old balloon. Maybe later. So we're going to take another balloon. We're going to try something else. Okay? And I think we've got hot enough water here. Not that balloon. That we're going to take this balloon. Now, remember how it took up less space? So we're going to put it in the nitrogen. And it's going to get cold. It's taking up less space and it creates a vacuum.
Is the white balloon going to start blowing up?
So the nitrogen is going to get cold and it's, crushing the bottle. The atmosphere is what's crushing the bottle. So the atmosphere, the pressure from the air on the outside stays the same, but the pressure on the inside goes down. All right? Now see how I sunk the bottle in there? We're going to put it in hot water. Now it's pushing it's creating more pressure. Might not have enough heat. Okay? Now if we take that off of there, And if we put some water inside here, now remember it floats, right? The nitrogen floats. I'm going to use different blue, it's not wet. All right, so we're going to put the...
You have twisted my powers.
Remember how it's building up pressure? So it built up pressure because it's evaporating, right? See how it's building up pressure? Now it floats on top, and I'm going to put this top on. You see how it pulls the bottom? So that's building up a lot of pressure.
Boys and girls.
See how the bolts? So this push bolts the bottle already again.
Boys and girls.
Now let's put it inside the bottle with no water. Now we're going to measure how much pressure is created by the evaporation. Now if this is 600 times more dense than water vapor in the air, there's 600 times more energy too. So there's 600 times more molecules coming in contact with the bottle if I put it in here. So therefore there's 600 times more heat coming from water than there would be from the air. So we're going to measure the different rates of evaporation. So we're going to put it inside there. You see how it's just not really doing much? Well, that's how much evaporation is happening because of the nitrogen, keeping the nitrogen inside the bottle full. Now we're going to pull it out, and the air now is starting to heat up the bottle, and it's starting to grow a little faster. And it starts to boil in here. Now if I put it in the water, remember that's got 600 times more energy. Right? So a lot more energy.
Holy cow!
Boys and girls, quiet down. Hey. Quiet.
Everybody likes it.
Yes! Come here, go challenge! Come here! Move! You have to come here. Move!
Hey, listen up.
On the outside, so as it transfers the heat, it throws the water.
Listen up.
Now we're going to do one last thing before we start to talk about ice cream. All right. No, that's all we're going to do with the robots.
Quiet down.
It's kind of funny how I get hired to blow stuff up in school. Yeah. So remember how, now I want to show you something. So if I put this water in there and I tip it upside down just like gravity, now there's some tension pressure keeping that in there, but it's not really pushing much out, right?
Yeah.
So if I take nitrogen and I put it in there, remember how it filled up a lot of pressure really fast? So the water is going to heat up that bottle that nitrogen. The water's going to heat up the nitrogen. Now, if I tip it upside down, the water's going to cover the cork. So what is it going to do? Is it going to blow up the bottle or going to push out the water? Push out the water?
That's enough. Back to your seats. Sit down. Hey! That's enough. Boys and girls, sit down. Be respectful of our guests.
I thought there was just a towel there. I did not realize there was a kid that needs a towel. I thought he was just holding up a towel. At least there's a towel. All right, so the last thing we're going to talk about is the crystal structure. Okay, so we have ice cream mix. So ice cream is made from milk. Milk is a liquid. Okay? What makes it a liquid? Water. Water makes it a
Boys,
liquid.
sit down.
The majority of water. Right?
down.
Water looks like this is the chemical structure. Okay, so it looks like that. So water looks like that. And so then, okay, but it's bent. You see how it's bent? Now the oxygen is the size of 16. Okay, and the hydrogen are the size of 1. So the oxygen is 16 times larger. Okay? So it's a lot bigger. Now if we take, I'm missing another slide. Okay, so if we take this, so if we take this, a bunch of these water molecules, there's a thing called hydrogen bonding, and it's a small bond. You can't see it with this very well. But if you think about like with that bent structure, and you've got the small pinky and small thumb, and the hydrogen bond breaks and forms and breaks and forms and breaks and forms. You have a question?
So hydrogen wants to connect with oxygen because I don't really know why, but for every hydrogen and oxygen, there's 2 hydrogen, and they like to link together, and that's what
They do, but then they break apart.
Yeah.
And so there's really 3 that are connected, but one of them's weak. And so it could be this one that breaks off and joins with another. And it's called hydrogen bonding. So the hydrogen bonding breaks and forms, breaks and forms. But you always got H2O, right? So you got the oxygen and 2 hydrogens. And as it breaks and forms and breaks and forms, that's what makes a fluid. Otherwise it would be a solid. Okay? And so as it gets warmer and warmer, those hydrogen bonds become weaker and weaker and they don't form anymore.
when it turns into a solid, it loses its energy, that's why it's moving slower. And when it's an gas, it has more energy, that's why it's moving the molecules are moving faster.
Right, but that bond also becomes stronger or weaker when it gets hotter. And as it gets colder, that bond becomes much, much stronger, and it doesn't break anymore. It starts to form a lattice structure. It looks like this. It doesn't matter. Same picture. So, but it starts out like this. So each one of those is like one of these. And they keep on growing. Okay, so now what does that start to look like? Snowflake. And that's why snowflakes form their shape, is because of that hydrogen bonding. And then they start to chain together and create snow. Okay, or ice. So you see the snow or the ice that forms on the side of the bowl? Okay, now, do you want small water crystals in your ice cream or big water crystals? Small. The smaller they are, the smoother the texture. Anybody had ice cream that's really, really grainy? Yeah, it's like really not very good, huh? So, well, I would beg to differ, but that's, if you like soft serve, but fine. I'm not going to argue with you, but the faster you freeze it, the smaller the water crystals. Usually it takes about 20 minutes to make ice cream. We take about 30 seconds. So the only way to get water crystals to form smaller is to freeze them faster.
Boys,
So you
back
freeze
up.
them faster, and the only way to freeze them faster is something colder. So to kind of give you an idea, you're going to take this, you're going to freeze a half a gallon at about 30 seconds.
Boys, back up. Boys, back up. Hey, knock it off. Back up.
See that? So down in our store in Provo, and then we have one out at the Port of the Valley.
Listen up.
Down in Spanish Fork. So this is how we do it. Every ice cream is made per person. So you walk in and everything is made per person. So there's nothing pre-made.
You can watch it happen.
You're gonna watch it happen every single time. So you get to choose everything about the ice cream. How hard you want it, how much fat you want it, whether you're lactose intolerant, whether you want Italian ice or not. We use a coconut base. Somebody lactose intolerant? No? Huh? You are?
I know, I'm just kidding.
Well, so I'm going to have the teachers come help me scoop.
Back up now. Back up.
And I'll start putting more.
Teacher's not here. Where is she?
This is O-Positive. This is our special recipe of O-Positive. I usually only have this at Halloween, but I figured kids love blood. It's really strawberries.
Hey, quiet down.
That's all.
Okay.